Hello and welcome. Today we're going to look at part 5 of chapter 19, Oscillations. So as we look here at our spring oscillating the mass back and forth, we see that there is energy involved. Okay? When we're at the equilibrium position, we're at the fastest. So that would be the maximum kinetic energy. And when we're at the maximum displacement on both sides, that is where we've got the most elastic potential energy. So if we had to draw a graph of this, we can see that at our maximum point over here, we have, because it stops, zero kinetic energy, but we've got maximum potential energy. And as we move it along, the potential energy decreases and the kinetic energy increases up to the point where we're at the maximum speed, which is at the equilibrium position. And then it starts slowing down, decreasing the kinetic energy, but increasing the elastic potential energy in the spring. So here we've got the most energy stored in the spring, with zero kinetic energy again. So on page 296 we see this graph where we basically see that if there is no external forces, no friction, we see that the total amount of energy in my graph stays constant, but it's constantly varied between kinetic and potential. So that was energy changes in simple harmonic motions. Next we're going to move over to damped oscillation. So on page 297 we find this graph under the heading damped oscillations. Now damped oscillations is what we will see in everyday life, where in almost every single case when there's an oscillation there is some external force, some friction or air resistance or something taking energy of my system away. And when we are taking away energy, we always find the shape of a graph keeping its frequency and its period, but the amplitude decreases. Now think of a child on a swing. You might begin very high and then the swing eventually goes until it stops almost again, but the frequency at which you swing to the left, to the right, and your pendulum would be exactly the same. So this is where we lose our energy due to an external force. Page 298 describes the effect that shock absorbers have on a car suspension, how the shock absorbers dampen the shock or the motion of the spring. So your car goes over a bump, the spring goes up and down, but your shock absorber returns your spring to its original position, okay, decreasing or dampening the simple harmonic motion created by your spring. In this case, your damping actually is very useful because the car would have uncontrollably jumped up and down. A way to test if your shock absorbers are still working or not is to push down on your car, and if the car bounces up and down for a few times, it means that your shock absorbers has stopped working. Next we will be looking at resonance. So most of you guys might have seen something like this before. Please look at the video, and if you try this at home, be very safe.
Hey, there you go. That's the first step. Down like a quarter step.
Yeah.
Okay. Yeah. Yeah.
It hurts a little bit.
Okay, and as you guys could see there, what happens was when you reaches a certain frequency, glass breaks. So in order for this to happen, guys, every object has a natural frequency. There must be a few things. We'll see that in some way a system, the glass in this case, is forced to oscillate. When forcing frequency matches the natural frequency, so when he sung at the right frequency, the amplitude of the oscillations grew dramatically. So then the glass started vibrating uncontrollably until it snapped. There are three things that need to apply. The natural frequency must be equal to the frequency of the driver or the singer. The amplitude is maximum, so that's the point where there's a maximum uncontrollable um, motion, and the absorption, it absorbs greatest possible energy from the driver. So as the driving frequency, the person singing increases up to the note, and you could see that how he used the straw to find that point. Okay, the tone that he should try, and then at that point the amplitude of the vibration of the glass spikes up, and that is where the glass breaks. Okay, now this is something similar that has happened in earthquakes. Okay, so earthquake, a building has its own natural frequency, and because the earthquake has the same frequency as the building starts shaking uncontrollably and start collapsing, especially in places where earthquakes weren't experienced before and the buildings weren't built to do that. Okay, so when we build buildings, we obviously don't want them to start shaking uncontrollably, and that is where we use damping. Okay, so we want to build the building so that the foundations absorb the shock waves. Okay, damping is thus useful to reduce the effects of resonance. Okay, and what we do is, if we have the effect, we can see that if we look at the green line, that is what should have happened. If we lightly damped it, we drastically decrease the amplitude where the uncontrollable shaking happens. And if we apply heavy damping, the amplitude is basically not felt at all. So then it won't collapse at all. Okay, so once we want to use critical damping. So critical damping, if we have a door swinging open and closed, the door will swing and come with a swing closed quickly without oscillating. Critical damping is the minimum amount of damping required to return an oscillator to its equilibrium position without swinging. Okay, so if we have um, our critically damped object, okay, we see that it only oscillates once and then comes to a stop very quickly. Over damping will be like, I think, the boys' toilet door in the college side that closes very slowly. For a place like a toilet door, you want it to go quite quick, but you don't want it to go to the opposite side. Now, under damping will create oscillation. Okay, so for example, they explain the example here of doors of restaurants leading to the kitchen that can swing in both directions. So critical damping will cause it just to close immediately. Under damping will make it swivel both ways until it eventually stops, and over damping will make it slowly close, which we also don't want. Okay, so we use resonance in a lot of places. We use it in musical instruments. We use it in microwaves where the frequency of the water molecules matches the frequency of the microwave oven matches the natural frequency of the water molecules in the food. Okay, so what happens is we make the water molecules move uncontrollably, so they absorb the energy and therefore they heat up the food. Okay, there's a lot of other applications to resonance. One of them is the MRI machine, where we use magnetic resonance imaging, and where we use different frequencies to make different tissues in your body resonate and creating clearer pictures of it. We're going to do a lot of this in chapter 32 when we get to medical imaging. Okay, and then a few big ideas here. So what they say here is this just provides us with a scenario of how ideas in physics really work. So scientists often take complicated problems like atoms in a solid vibrating and reduce it to more simpler examples or problems like an oscillating spring. They test this until they get a workable theory. Then, if they can get a formula for that, they feel much happier, and they use that to solve the problem. Once they've solved the problem, they take their solution to other problems that are similar, and then they keep on modifying their solution until it fits a wide range of solutions. What happens if a vibrating mass experiences a frictional force as it oscillates? Okay, so there's a question here which is based on our initial problem, and then they start applying it to many other situations as well. Okay, I hope that the section has not left you too confused. I will make a video or two of how to apply the topics in this section. Thank you.